So after having understood how to set up the principle of minimum potential energy or the total potential energy to set up the finite element formulation, we came up to the point of where we would just set up the equilibrium conditions. So we did a minimization, which was basically the setup of the equilibrium equations. I want to go one step ahead and actually show you the formulation for a single arbitrary element. So this is just the kind of element we've already been working with, so it's nothing complicated. I'm going to just use a spring element again. I have two nodes. The element has a stiffness of K, which is given as EA by L. We have already established this many times, so I'm not going to go through it again and again. We can also just consider it as a simple element, not a spring, but just a element with a single degree of freedom. So basically it has a degree of freedom ui here, because this is node I and this is node, let me call it I plus 1 to keep uniformity with the nodes, and this is ui plus 1. So if you remember, I'm still going to recollect it, I'm sure you do. We had set up the strain energy for an element, which was given as the volume integral of E epsilon square by 2 differential of the volume. And at the same time, we had set up the work done externally as a summation of Fi ui. Okay, now the work done externally is quite simple. So if you consider that this element is a part of a system at which there is a load acting on a certain edge or whatever, and it has only 1 degree of freedom, then there are, if you just make the free body diagram, then you know that there is a force Fi acting here and a force Fi plus 1 acting here, just for equilibrium purposes, yeah, for a free body diagram. So the external work done can be quite easily written as Fi ui plus Fi plus 1 ui plus 1. Nothing complicated there. So I'm just writing it out and getting it out of the way. Now let's get to the strain energy. The strain energy equation consists of one quantity here which we can define, which is given as the strain. So the strain in the element can be easily defined as, it's not equal to, so the strain in the element can be defined as the difference in the displacements in the both sides. So ui plus 1 minus ui divided by the length of the element, which is also known to us is L, because I already defined the stiffness. So ui plus 1 minus ui by L. So that's the strain in the element. So the chain difference in the displacements between node I and node I plus 1. Of course, that's going to give you the deformation caused due to the force acting. So there we've defined the strain. We just have to substitute this strain back into the strain energy, which gives us strain energy to be equal to volume E ui plus 1 minus ui by L whole square by 2 dV. Now here we can write dV as a dx, because dx is the only dimension that's actually changing with deformation, and the cross-sectional area A always remains constant by our standard assumption that we have made for this element. So if we just go back to substitution, then it has to be over dx. We can write EA by 2L square for all the constants to the left, and then expanding the contents of this simply by using the basic rules, dx. Of course, if I have to integrate dx over dx, I get x, and x can be replaced with limits. So instead of writing here x, I can also just write the limits as 0 to L. And this 0 to L, when I substitute, if I integrate, I get instead of x, I will get dx, I will get x, which can be substituted as L minus 0 for the two limits, which will remain with L, and that L can be cancelled out with 1 L over here. So what I will get after the integration is EA by 2L ui plus 1 square plus ui square minus ui plus 1 ui. So that's the content or the equation that I have arrived at, the relation for the strain energy in terms of the two displacements. Now we have two displacements here. We already discussed that we have to minimize it for the two displacements. Now we already have the external force defined and the strain energy. I'm not going to write it together as total potential energy because it's just writing exercise. It doesn't really bring much. So if I now find the minimum of the strain energy separately and the external work separately and put it together, I will get the same equilibrium equations that I'm looking for. So let me do a minimization with the two displacements as mentioned here for the strain energy. So the strain energy first with Ui will be given as Ea by 2L becomes 0 plus 2Ui minus 2Ui plus 1. So I can get the 2 out, and what I'm left with is Ea by L Ui minus Ui plus 1. And then in the second case, I have the change differential of Ui plus 1 is equal to Ea by 2L 2Ui plus 1 minus 2Ui is equal to Ea by L. Of course, the 2 is again going to cancel out, and I will get minus Ui plus 1. I'm writing it in this way because then I want you to see the obvious in these equilibrium equations for the first part. Now once I have these two equations set up for the minimum of the strain energy, I will also do the same for the minimum of the work done or the external work done. So the minimization of the external work done, WEXT, will be given as, so if you remember the equation, it was W is equal to FIUI plus FIUI plus 1 Ui plus 1. So this will be, you will only be left with Fi. And when you do the minimization with respect to the other displacement, you will get Fi plus 1. So if now you put the total potential energy together as pi is equal to the strain energy of the element minus the work done externally, then you will get quite easily, well, I don't want to write it on this side, I'm going to go back here. So I will say the total potential energy of the system will be given as Ea by L Ui minus Ui plus 1 is equal to, or in this case I will write it as minus Fi is equal to 0. And the second equation for the second minimization is given as minus Ui plus 1 minus Fi plus 1 is equal to 0. So these are the two equations that you need here. So I'm going to call them, let's say, A and B, because I already used numbers before. And in this case, I can see the obvious. Of course, I've already defined before that the equivalent stiffness is given as Ea by L for all the other problems as well. So this can be easily replaced with a K equivalent or just a K. And then I have the two displacements now and the two forces. So I can write this in a matrix notation where I can say it is K times, for U1 I get 1, for U2 or Ui plus 1 I get minus 1, and the same way I get minus 1 for U1 here, Ui, and Ui plus 1 is 1. So therefore I must multiply it with the vector Ui and Ui plus 1. And this is a negative sign, so I can take it to the opposite side of the equation, and I can write this also in a vector format as Fi and Fi plus 1. So this looks exactly similar to the other equations that we have defined for every element. For a single element with a single degree of freedom at each node, we can get the same equilibrium equation. So if I just write it in a simpler format, I will always end up with this as my equilibrium equation, which is also used for the finite element method. So this is just the formulation of a single element. You can easily come up to this point, then you use the same equation to set. So this is the local stiffness matrix. Of course, you know this is the stiffness matrix. This is the displacement vector, and this is a force vector. So you can set this up for every element and then put it together to form a global equilibrium equation as I've shown you before with the direct stiffness approach. The reason why I wanted to do it with just one approach is that we ultimately always come back to this particular equation, and all we need to do is basically use it for every element again and again, and then make a global system. So that's the reason why I'm asking you to rather program it in MATLAB, C++, Python, whichever one you like to use. So at least you can get all these things done in a simple way for a single element, and when you change the input, it just gives you for multiple elements, and then you can just put it together. So that's the basic idea I wanted to put across by using the minimum potential energy approach.